let me give an economic example of the total differential. How many of you had intermediate micro? Okay, a lot of you have. Do you remember talking about production isoquants? Okay. What is a production isoquant? A production isoquant shows all the different combinations of two inputs capable of producing a given level of output. So let's take this case right here. The most common case is this. Let output be a function of capital and labor. If you fix output at a certain level, Q sub 0, then an isoquant would just be all the different combinations of capital labor capable of producing Q sub 0 units of output. And you could draw it in a diagram that looks like this. A typical isoquant would look something like this. Let's measure labor input on the horizontal axis and capital input on the vertical axis. Then what an isoquant would show is all the different combinations of capital and labor just capable of producing this output level of Q sub 0. John, Q sub 0 could be, say, 100 tons of steel per month. Okay, so we could let Q sub 0 be 100 tons of steel per month. Then this curve would show at point A, you could use this much capital and this much labor and just produce 100 tons of steel. Or this, you could use this point right here, point B, which corresponds to using this much labor and this much capital. In fact, there might be like an infinite number of points along this curve, a nice smooth curve, showing all the different combinations of capital labor capable of producing 100 tons of steel. Now, if you wanted to produce 200 tons of steel, then obviously you'd have to use more capital and labor, and this isoquant would be further out. So if we let Q sub 1 be 200 tons of steel, it might look like this. These isoquants are going to have a negative slope because if you use more labor, then you can use less capital to produce the same level of output. So they should always have a negative slope. And typically, they'll have this convex shape. They'll be bowed in towards the origin. Okay, so that's what a isoquant is. Now, let me relate this to the concept of a total differential. If you have a production function like this, Q equals F of K and L, then and in economics, this function is just called the production function. Okay. What would the total differential of this expression be? If we were to take the total differential of Q, it's called dq. What would dq equal? Right, so it's partial F, partial L times dl. Okay, the change in labor is dl, plus, okay, partial F, partial K times dk. Okay. Anytime you have a dependent variable that is a function of two independent variables, the total differential will always take this form. Here, we're putting this one first, partial F, partial L times dl plus partial F, partial K, dk. Okay. So anytime you have a function of two variables, the total differential will be expressed this way. And this partial derivative here, partial F, partial L, in economic terminology is what? Jana? The marginal product of labor. Okay. Partial F, partial K in economic terminology is? Okay. So the total change in output is just the marginal product of labor times the change in labor plus the marginal product of capital times the change in capital. Partial F, partial L is the same thing as partial Q, partial L. So if you find it more convenient to use this notation, that's okay. Because a Q is equal to F. So that's an alternative notation that you could use. Yeah. Yes. Yes, a dq is just the total change in output. So it actually makes sense. The total change in output, it's like a delta Q.
Okay, so we don't need to say like with respect to anything.
Right, because see, it's different from a derivative. A derivative is the ratio of two differentials. So dq is just the total change in output. See, actually this makes sense. What this equation is saying in words is the total change in output is equal to the marginal product of labor times the change in labor plus the marginal product of capital times the change in capital. Now, what would happen if, say, dk is 0? If dk were 0, then that means capital's not changing. And what would this equation reduce to then? I've forgotten your name. Lydia, yes. Then if dk were 0, Lydia, what would this equation reduce to? Yeah. Yes. And so this term would just drop out. So this would be equal to partial F, partial L, dl, because dk is 0. Now, suppose you divide both sides of this expression by dl. Then what do you get? You would get dq dl equals partial F, partial L, which makes sense because you're holding capital constant. So then dq dl is just the same thing as partial F, partial L. And then you could just determine this ratio would just be the partial derivative. Because it makes sense because you're holding dk constant. And then that's, the equation makes perfect sense, doesn't it?